In section 711, we're going to mathematically describe the movement of gas particles based on absolute temperature and mass of the gas. Specifically, we'll do this by starting with the equation for kinetic energy to derive the root mean square speed equation, picking up the concepts of diffusion and effusion along the way. Let's begin. According to postulate 5 of the kinetic molecular theory, the average kinetic energy of gas particles is proportional to the Kelvin temperature of the gas sample. That means the average kinetic energy of gas A is equal to the average kinetic energy of gas B at that temperature. This allows us to generalize, stating that the average kinetic energy of any gas particle is equal to the absolute temperature times a constant K. This constant has been experimentally determined to be equal to 3/2 R, the ideal gas constant, in its energy form, where it's equal to 8.314 joules per mole Kelvin. Dropping this definition of K into the average kinetic energy of a mole of gas particles equation gives us Ke equals 3/2 RT. What if we wanted to find the kinetic energy of a single gas particle rather than of a mole of gas particles? To do that, we'd take our kinetic energy equation and divide it by 1 mole of particles. Recall that we've also seen a method for calculating kinetic energy in Chapter 6 as a function of mass and velocity of a particle. Let's look at what that means for particles with a range of masses, all at the same absolute temperature. At a given temperature, all gas particles will have the same kinetic energy. If we graph the average speed versus the mass for the series hydrogen, helium, water, and oxygen, it becomes clear that those particles with smaller masses have faster average velocities. What happens if we vary the temperature? As we just saw, gas particles with very low masses move faster than gas particles of higher masses at all temperatures. If we hold the mass constant and instead vary the temperature, as we've done here for a sample of nitrogen molecules, we see 2 trends. At low temperatures, the speeds of all gas particles are close to the average speed, with a narrow range above and below the average. As the temperature increases, however, the range broadens as the average speed increases. If we combine the 2 equations for kinetic energy and solve for the velocity, we see velocity squared is equal to 3RT over the mass of an individual particle, m, times Avogadro's number, n sub a, which is easily replaced with the molar mass, m. Taking the square root of both sides gives us the root mean square speed, v_rms. By definition, v_rms is the velocity of particles possessing the average kinetic energy in a gas sample of known molar mass. We've seen R be pretty bossy in terms of which units we can use, and the root mean square speed is no exception. Joules are actually a derived unit, so breaking it down into its component parts, we see that 1 joule is equal to 1 kilogram meter squared over seconds squared. The direct consequence of this is that we'll need to translate the molar mass of gases from grams per mole to units of kilograms per mole. Let's see how that works. Let's calculate the root mean square speed of nitrogen molecules at 25 degrees Celsius. Following the unit conventions required by R, we need the temperature in Kelvin and the molar mass of nitrogen, 28 grams per mole, converted to kilograms per mole. Dropping these values into our equation, we get v_rms equals the square root of 3RT over m. v_rms equals 3 times 8.3145 kilogram meter squared per second squared per mole Kelvin times 298 Kelvin divided by 2.8 times 10 to the negative second kilograms per mole. Eventually, we see that nitrogen molecules travel at an average speed of 515 meters per second at 25 degrees Celsius. To wrap up our discussion of the movement of gas particles, we need to introduce the concepts of diffusion and effusion. Diffusion is the process by which gas particles spread out to occupy the entire volume of a larger vessel. Diffusion depends on the temperature, the mass of the particle, and collisions with other particles. The number of collisions is dependent on the pressure of a gas sample, as higher pressures will result in a shorter mean free path and therefore more collisions. If you'd like to see diffusion in action, take a minute to review this video from section 711. Diffusion is the escape of gas molecules through a tiny hole into a vacuum without collisions. Figure 7.25 has an excellent activity that lets you explore the effects of temperature and molar mass on the velocity of particles. Let's look at the mathematical side of this activity by comparing the root mean square speeds of two gases simultaneously. Graham's law of effusion allows us to compare the ratio of effusion rates of two gases as the inverse ratio of the molar masses. I'd derive the equation, but I don't want to risk you falling asleep, so let's put it to work instead. Let's calculate the relative effusion rates of helium and oxygen. Using Graham's law, we see the ratio of the root mean square speed of helium to oxygen is equal to the square root of the molar mass of oxygen divided by the molar mass of helium. This result tells us that helium atoms effuse at a rate that is 2.83 times faster than the effusion rate of oxygen molecules. This makes sense because helium weighs a lot less than O2. A gas known to have a formula of NOx was found to effuse at a rate that is 0.834 times the rate of effusion of oxygen. Determine the molar mass of NOx and the value of X. Given the effusion rate of 0.834, NOx must have a higher molar mass because it effuses more slowly than oxygen. Plugging in values and solving for the molar mass of NOx, we get 0.834 equals the square root of the molar mass of oxygen over the molar mass of NOx. The molar mass of NOx is 46 grams per mole. Using the molar mass of NOx, we see that 1 times nitrogen plus X times the molar mass of oxygen equals 46 grams per mole. Solving for X, we get a value very close to 2. So NOx is actually nitrogen dioxide. I'll leave you with the parting thoughts of the authors.